Hi, my name is Hua Zhong. I'm a SVP of engineer from WeRide. I'm an engineer, so the topic is transform urban living with robobus. But I have some technical contents inside, but not that deep because I know the audience here are not everyone is an engineer. So let's begin. This is a picture we took in Las Vegas in I think the year before last year, CES. I like it because the sky's color is really nice. First, I will talk about why we built this robobus. A lot of people said autonomous driving can relieve the traffic jam in the city, but actually that's not true. The only way to reduce the traffic jam is actually through public transportation or carpooling, because no matter the vehicle drive itself or drive by a driver, it doesn't reduce the traffic, the volume of a city. Only by carpooling or use more public transportation can you reduce the traffic jam. Comparing to private cars, the public transportation has some shortcomings. The first one is like the waiting time. You have to wait the next bus. But for private car, you just go anytime you want. So to reduce that waiting time, usually you can increase the shifts or increase the number of vehicles. And the second is there are many stops, but not every stop is your stop. For private car, you just go from door to door. You only stop once. The way to reduce this shortcomings from you only stop in major hubs. And another one is the working station. You have to work a long distance from the station to your final destination. Actually, that part, make a lot of people choose private car rather than public transportation. The only way to solve this problem is you have more cars, more buses, more routes to cover more areas, but that requires a lot of investment, let's say. And in many cases, that's too expensive for many public transportation operators. So to make it better, I think now many people think it should be a tiered network. That means there's a backbone. It's a train or really big buses or tram or subway. They have really large capacity. Hundreds of people can take one train, and they have fewer stops. They only stop at the major hubs, and of course they have fixed schedules. Usually, this kind of major hubs can reach within 1 to 2 kilometers of your final destination. But that's not enough, because the last mile or last 1 or 2 kilometers, how do you cover that? So there's some local coverage. I have seen many cities have began to have this like a local coverage. They use mid-size or mini-size shuttles to go within like 200 meters of your final destination. So that's much more attractive for people to give up their private car because it's so close to your final destination. Usually these shuttles have a small capacity. They have more stops. Sometimes it's even on demand. That means they go along a route. Whenever you want to stop it, you can stop it. When nobody wants to stop it, it just keep going, so you can reach your final destination faster. And they have short waiting time. For example, what we run in China is the shuttle run a fixed route. Every 5 minutes, you have a shuttle coming to your stop. So you have really short waiting time. In Europe, we are working with some partner in Switzerland. We have this rural or suburb coverage. We use even smaller size of shuttles, like a passenger car or passenger van. It's fully on demand. the purpose is to bring people from their door to the train station so they can give up their private car to fully use the public transportation to go to the city center, work there, and come back home. So that's a tiered network. But the thing is, in order to have local coverage and rural or suburb coverage, you need a lot of vehicles. That means you need a lot of drivers. And I think everybody here, you know how difficult to hire public transportation drivers. I know even in China it's the same, because a public transportation driver, they have a higher standard. So it's even more difficult than taxi drivers you can hire. So that part actually make a lot of this plan, not viable or too expensive. So here comes, I think, the autonomous solution, because we don't need driver anymore, just the vehicles. And I think this is the only viable and economical solution for this tiered public transportation system. In the background, we still use trains and big buses or big tram, but local coverage, we use autonomous driving vehicles. And here is our solution. We have several different type of vehicles to help build this tiered solution. First one is a 8.5 meter long bus. It has about 25 seats. Later I will talk more about the details. This is the latest version. We are still in development. The middle one is the one we just took ride today. It's 6 meter long, have 10 seats. Well, the version we took today have 8 seats, because it's modified to be able to install a steering wheel because of the homologation stuff. But if we forgot about the steering wheel, we can make it a 10-seaters. And the third one is a 5 meter long van. It has 5 seats. It can be running like on-demand shuttles for the rural or suburb area for the coverage. So the big bus, 8.5 meters long. This is our prototype. So we're currently working with the public transportation company in Guangzhou, where our headquarters is. We estimated by deploying this autonomous driving truck, even in China, we can save about 18% of the operational costs. We know the drivers in China is relatively lower cost than the drivers here, but even in China, we can still save the operational costs. And after the pandemic, a lot of public transportation company or the cities, they run out their fundings. So this kind of savings for their operational costs really make them very, very attractive to a local public transportation company. So we hope in this year or early next year, we can release this bus. We can begin to replace normal buses from the public transportation companies every year. So maybe in the first year, 5% of the vehicle will be converted to autonomous driving, and then we continue to increase the percentage. And the minibus actually is our first product, because this one is smaller. Technologies we use in this one is more close to the robotaxi we developed. Basically, we use the exactly same technology. We just copy and paste to this vehicle. So the idea is to use this one to connect the subway stations to passengers' final destination within 200 meters of the final destination. So this vehicle can run at top speed of 40 kilometers per hour. We have the Gen 2 version that can run 69 kilometers per hour. That's the speed limit for all public transportation vehicles in China. So it can replace any existing vehicles in the open roads. And this one, the design is there's no steering wheel, there's no pedals. Of course, you can put a temporary one there in order to emergency, control of the vehicle, but usually there's no steering wheel at all. So, and I think everybody has experienced that, so I will not say too much about it. And this is the on-demand shuttles we developed with a Chinese OEM. It's designed from the ground for level 4 operation, so it has fully redundant chassis and everything we need. And we released this vehicle, I think, last year. This is in China we use that for taxi purpose, but it's also can be used in the rural or suburb coverage for public transportation purpose. Actually, we're working with Switzerland, some of this similar vehicle, but this particular one. But we hope this one may provide better service for that purpose. So that's the production we have. And next one, I will talk about the technology. So this is the engineer part, but not that deep. I think everyone can understand. So basically, we use all the state-of-the-art setup for safety and performance. For example, this is our mini shuttle. So we have a lot of sensor there. They have 360 coverage all around the vehicle, and there's no blind spot. All the blind spot has been covered by two kinds of sensors, LiDAR and camera. So we have this mid to long range LiDAR. They can detect objects farther than 200 meters. And then we have the close range LiDARs. Because this long range LiDAR, they have blind zones close to the vehicle because the viewing angles. And then we have the close range LiDAR. They can see anywhere from 0 to 30 meters. And also we have the camera, similar coverage for cameras, mid to long range for 200 meters and close range fisheye cameras to cover 0 to 30 meters. And also we have GPS RTK units to have high precision localization for the vehicle. And also around the vehicles, if you can see this bands, that's not for decoration. It's actually collision sensors. So whenever there's some collision happen with the vehicle, the hardware, the sensor can detect that. So the vehicle can stop to prevent any secondary damage. So this is the sensor setup for our minibus. For our larger bus or all our next generation vehicles, we changed it a little bit. First, we began to use a solid-state LiDAR. So the current one, we still use a mechanical rotating LiDAR. It has 360 coverage, which is good, but the solid-state LiDAR is much smaller. It has better performance and it's much cheaper, which means it's better and cheaper. So we have this long-range solid-state LiDAR can detect objects up to 250 250 meters with 10% reflection rate. Basically means it's a vehicle's tire is totally black. We can detect it in 250 meters. And then we have the close-range flash LiDAR. So flash LiDAR is also a new kind of LiDAR. So it's much cheaper than mechanical rotating LiDARs. It's very good for close-range detections. So our blind spot or close-range LiDAR becomes the flash LiDAR. It can detect the objects from 0 to 20 meters. And we also have collision sensor. So the collision sensor will be similar to the one we have, but we add another layer of redundancy. So not just the band sensor, we also add accelerometer, or we could say it's an IMU behind all the panels. We can detect sudden change of acceleration. That means if anything collision with the vehicle, we can detect that. And for the mid and long range camera, we actually increase the resolution to 8 megapixels. So we can see objects up to 250 meters. And of course, we also have fisheye cameras to cover the short range from 0 to 20 meters. We have similar GPS units as well. So, but you know, this vehicle is longer. So in that sense, we have more cameras and a little bit more LiDARs to cover the close range areas. So the vehicle itself is working with a Chinese OEM. You know, for this large vehicle, in order to have a drive-by-wire system, not only drive-by-wire system, but also redundant drive-by-wire system is kind of difficult. So before we only have smaller size vehicles, but now we have this redundant drive-by-wire system for large vehicles, and then we begin to move to 8.5 meters vehicle now. For the objects very close to the vehicle, I mentioned we have this fisheye cameras as well as this close-range flash LiDARs. The close-range LiDARs actually installed here, and the cameras, they're kind of looking down. The FOV, the field of view, the closest one is almost vertical. That's why we make it, protrude a little bit. That's because we want to see exactly what happened here. So there's almost zero blind zones around the vehicle. In that sense, actually, we can see everywhere. And we have to, before we release this sensor setup, we did the simulation. So a 1 meters high a child, standing exactly next to the vehicle, and we can see more than 60% of the child. So we can see it. So for the blind spot LiDAR, actually we have 4 of them. 1 in the front, 2 on the side, both sides, and 1 on the back. So everywhere there's no blind spot. No blind spot. And all the areas covered by 2 kind of sensors, not only by LiDAR but also by camera. So that means in some extreme case, 1 kind of sensors malfunctioned. For example, in a pure dark environment, the camera actually cannot see anything, but the LiDAR can still see things there. So it's fully covered. The gap between the curb and the vehicle, it's not because we cannot see the curb or anything. So I think mainly because when there's some people standing by the curb, usually our vehicle will give some paddings, not very close to that. So I think technically we can park very close to the curb if we want. Yeah. To avoid an object, it's not just stopping, but also you can steering away from it. In most cases, if it's very close, you can steering away. But even for stopping 250 meters for 69, I cannot remember exactly the number. There are quite a few seconds you can stop your vehicle. If you only use a braking system, that is still capable to do that for this kind of vehicle. The computing units is very important for any AI running in the system. So the current version we use, we call HPC high performance computing units 2.0. That's our Gen 2 units. It has 1,000 TOPS of AI computing power, but it consumes a lot of energy. The peak energy consumption is about 1.6 kilowatts. And also we have a redundant units. It's a reduced power units just to make sure when something happens to the main unit, the redundant units can support a vehicle to do safe pullover. So it has about 250 TOPS of AI computing powers. The second half of this year, we will release our latest version of computing units. We call it HPC Gen 3, 3.0. It will double the computing power to 2,000 TOPS, but reduce the peak power consumption by almost 2/3. So back down to 500 kilowatts. 500 watts, and everything is auto-graded. So it's SOD rated units, has some higher reliability and really high computing power. We still have the similar redundant units. That's our, and these are more detailed about different generations of computing units we have. So at the end of the year, this year, we will switch to HPC 3.0. So it will be very powerful but consume less power, and more reliable. Yeah. And the very important thing about the autonomous driving is the safety. And a lot of safety coming from the redundancy. So the redundancy is not only for the vehicle itself, but the whole system. So this is a very simplified description about the redundancy design we have. It's from the sensors. So we have, as I mentioned, we have two kind of sensors to be like the backup for each other. And for each kind of sensors, LiDAR or camera, their FOAs also have some overlaps, so that any single kind of sensors, they can also be the backup to each other. So that's the sensor redundancy design. And for the network, because our vehicles, in many countries, it required some remote monitoring for any autonomous driving or driverless vehicles running in the public road. So we need to have a very reliable network connections. So our design for networking can have up to 3 redundant connections from 3 different ISPs to ensure very high availability of network connection. And then it's the computing units. It's like the brain of autonomous driving system. As I mentioned, we have 2 units. One is the main unit. One is a reduced powered redundant units. So we can make sure if the main units, even though it's a highly reliable units, SOD rated, when it fails, we still have a redundant units, which is also a auto-graded computing units to cover the whole thing. And then it's the DBW's drive-by-wire system, actually connecting the brain of the autonomous driving system to the vehicle. So we have a dual setup, mirroring setup, so the connection is also redundant. And eventually going to the vehicle itself. So the steering and braking and the communication as well as the power supply. We require the base vehicle have all the redundant drive-by-wire system, those actuators as well. So that's why we spend a lot of time working on the vehicles, because normal vehicles, they don't need this kind of redundancy, because the ultimate redundancy is the driver himself. So they don't need a 2 set of drive-by-wire system. So that requires an OEM and add additional parts, hardware and software to implement that. So overall, from software system to sensors to computing units and everything is redundant in our vehicles. And the performance, of course, our algorithm is designed to cover end-to-end urban scenario. That means from your position, from where you start to where you go, everything will be covered. This is some typical scenarios we said we can handle, but basically everything happen in an urban area, we should be able to handle that. Okay, so for the minibus, it's a very mature product from WeRide. Already we have deployed in more than 30 cities, and we have been doing this public transportation operation for more than 5 years. And we have deployed more than 300 vehicles in 7 different countries. And I think at the end, I have a short video to show our bus. Yeah. Guangzhou is our headquarters. So. This is in Abu Dhabi. This is in Vegas. and in Singapore. This is last year. All right. Okay. Do I still have time?
Thank you very much.
Thank you.